photosynthetic complexes, detection and interpretation challenges, please.
Yeah, thank you very much. I just realized when I look at the title that it's not clear that I never did a single experiment here. So it's going to be theoretical talk, but in the introduction part I will overview this recent, very exciting and very puzzling to me experimental results. And I also try to outline what is so puzzling, and I'm still not sure how to interpret it, and that's why I call it like challengers, but maybe there will be some ideas or some answers, so I'm expecting answers from you. I'll be asking a lot of questions. So this is a kind of outline. I'm not sure that I'll be able to talk about everything, but in the introduction we'll overview the available biological 2D photonic experiments. And another important thing to maybe again to look at is this exciton model, which has been employed to interpret it. Yeah? So it's the model which is always behind these interpretations. And I will mention the method which we use for the calculation of the signals. And I will try to also maybe give the ideas why two-dimensional Photon-Echo, how it works, and what we get for the exciton model if we calculate the two-dimensional spectra, and how well or how bad it compares to the experimental. There's a number of open questions. We'll see if we have time to ask them. So this was not the first experiment on the phenometric also complex, but the first experiment where the oscillations were detected. This one is, yeah, okay. So these are 2D graphs and these are the oscillations, and this we have just seen in the previous talk. So this is the lower diagonal peak exhibiting a number of frequencies. And this is interpreted in terms of these exciton energies, and they all contribute to the diagonal peak. It is an under-phasing contribution, we all agree. At that time, it had been published that they have detected also kind of the same oscillations for the lower cross peak, which is 1,3 here. And you see again a number of frequencies. And when I saw this result in 2007, I immediately thought these are not excitons, because if you would look at one particular cross peak of the two-dimensional spectra, and I will try to explain why later, then what you expect to see is just one particular frequency. And then we have a number of frequencies here, so our initial idea was, well, there must be some vibrations involved, or something like this. This you also have just seen. These are now 2010 results on the same system, looking at the same cross peak. Just correct me if I'm wrong. And now we're all happy to see one oscillation only.
Noise is up. It is much, much better.
Okay, good,
New
great.
experiment.
So now this must be now what I have to believe into here. So this brings me back to the concept of excitons, and that's why I will be mostly talking about the exciton model in the following. What I don't understand here, and I didn't have time to ask you, maybe you can explain it to me, is this exponential decay. Is it kind of normalization you introduce, or?
It's we attribute that to primarily the spectral diffusion in the system, that you lose your rephasing capability.
Okay, well, just because maybe we can't account for it, but just because from everything we ever learned about two-dimensional spectroscopy, when we look below the diagonal, we expect the cross peak to grow with time. And here it just disappears, so that's something which I can't reproduce and can't bring.
If I normalize each spectrum to the maximum, it grows.
But you can't normalize each spectrum to the maximum, because
That's why
then
you see the decay.
you would probably not see them on the oscillations. if you normalize each scan. So this is still something which I would like to understand better, so to say. And that's why, because of this controversy in the experimental results, it's not criticism, it's just that I don't know what I can trust. Yeah? I also put here the very first results on the same system, the same complex. At that time, there were no oscillations reported, but there's still some differences, yeah? Even between the two-dimensional plots. So I'm in need now, as a theoretician, I'm in need for something which I can really compare my simulations to. Yeah? So I just really want to know what I can trust. But that's just a question. So what we know about now quantum, about the FMO complex from two-dimensional spectroscopy, really beautiful experiments. And it's been keeping me busy for 2 years already. It's really great. So there are cross peaks, yeah, that's what we know, and there are coherent oscillations on cross peak intensity, and I would say there is a natural temperature dependence. So we have broadening, and we have faster decay of the oscillations with temperature. So now the question is how to model this complex in order to understand it. And actually, if we understand it, maybe we can also use these ideas to understand results on other photosynthetic complexes, these LGS things at ambient temperature. Again, what we really see are cross peaks and oscillations. This is what we believe, and they exist. Well, here's 300 femtoseconds, but it's ambient temperature. Things are there. Maybe there are other photosynthetic systems to come to exhibit cross peaks and oscillations. Who knows? So excitons. We start with very, in order to understand them well, we start just with very simple case. The simplest case is what is normally referred as a diamond model. Just consider you have two-level systems, yeah? And each two-level system represents a molecule, ground state and excited state. And then imagine you have a coupling between the excited states of these molecules. So what happened when you diagonalize the whole Hamiltonian? Oops, that's a wrong picture. Well, actually what must be here is another picture showing two excited states. I'm sorry for this. Anyway, so what you get from this two-level system is one ground state, common ground state, and then two excited state. I don't know why one has disappeared from this slide. And now, how people have been thinking about the FMO complex, about this huge complex, they would get monomer out of the trimer, because they would say that the interactions here are pretty weak, and we can consider only the monomer. And then out of this, they would get the 7 bacteriochlorophyll molecules, and each molecule will be a two-level system, ground and excited state. All the excited states will be coupled, so what happens? We form a system of 7 excitons. There's a certain ground state, and nothing is excited, and then there's 7 excitons. So the whole complex is just modeled this way. And the question is how to describe environment. So only electronic degrees of freedom are taken into account explicitly in the system part of your Hamiltonian, so to say, and then you think how to model the environment, because you need the environment in order to induce population transfer, in order to get down to the lowest state, to have this energy transfer in this excited system. Well, now let us have a look at exciton dynamics. And, well, that's pretty intuitive. What is compared here is, these are the results of very simple treatment when you would use only rate equations. So there is no coherence transfer here, there is no coupling between populations and coherences. There are just certain rates for the populations to decay. When we say populations, we mean diagonal terms of the density matrix in the exciton basis, yeah? And then some dephasing rates for the coherences, so that each coherence would decay with a certain rate, and population transfer would bring the whole energy some point to the lowest exciton state. And you can have a look at their if you can, and the population in the side bases, and then you will have oscillations. So if you look at the excited state of each molecule, then you will see this oscillating motion because you have prepared coherences, so you have prepared also octagonal terms of your density matrix. The initial condition here that close to experimental ones, so we just introduce a certain pulse, I think about 30 femtosecond, to excite the whole system. Now we can do the full Redfield to describe the same dynamics. That means we have now also the coupling between population coherences. So you see down, these are populations in the exciton basis, so diagonal terms of the density matrix. Actually, the general behavior is very much like, the rate at which you have this energy transfer and this transition, this intermediate state gets populated and so on, they're very similar, and there's not many differences. Well, there's some slight modulations in the populations because there's a coupling to coherences. What is interesting that here there's several coherences plotted. And what is interesting that each coherence has a different dephasing rate. So if you look, the red line, for example, is our 1,3 coherence, which also people look in experiments at. And in this particular treatment, it seems to survive in the longest time scale. Again, in the side basis, if you look at the excited state of each individual bacterial or molecule, there's not many differences if you compare the two treatments. Okay, so now why two-dimensional Photon-Echo and how it works. Two-dimensional Photon-Echo is a 4-wave mixing scheme. That means that you have 3 laser pulses, 3 incoming laser pulses. They would interact with your sample. And then the Photon-Echo chooses a particular phase matching condition, and in order to calculate the signal, you need a way to calculate the induced polarization in this particular phase matching condition, or obviously in this particular phase matching condition. This is again an overview. What approaches exist. There is the most famous Muhammad approach, which uses perturbative treatment of the system field interaction. It's a very clear approach. However, it may get really hard to calculate response function for complex system Hamiltonians. There's always an alternative. You can calculate everything non-perturbatively and just put your system field interaction to the system Hamiltonian, also somehow add it to the commutator. Then you automatically account for pulse durations, pulse overlap effects, but there's a drawback that you have to analyze the total polarization, because what you get at the end of this simulation is the total polarization, and you have to analyze it to get back to some particular contribution which you need, for example, for your Photon-Echo signal. What we've been developing in the recent years and applying in the recent years is the so-called equation of motion phase matching approach, with the purpose to combine the advantages of the perturbative and non-perturbative treatments and still remain computational efficient. I don't know if I have to go into details here. I think I will skip a couple of slides and just will try to explain you how this approach works. So imagine you have an equation of motion for a certain density operator. And in a normal non-perturbative approach, we just add this interaction term, which is a system field interaction, to the commutator, and then you might have some relaxation here. Okay, that's fine. So what happens in the equation of motion approach is that instead of solving this equation, you simultaneously have to propagate 3 auxiliary equations for some operators which you introduce, and instead of the system field interaction here, you put just some parts of this system field interaction, because your system field interaction has 3 pulses. What I mentioned in the very beginning, Photon-Echo is a 4-wave mixing scheme, so you need 3, where I am, here. So you need 3 interactions with the incoming field, and then you can show that doing this 3 propagation instead of solution of your equation of motion, then you can calculate the particular contribution of the nonlinear polarization you you need just using these auxiliary operators. Good. Now you can also formulate it for the wave functions, but this is I also skip. Again, several words about Photon-Echo, and we just try to remain as simple as we can here. So we have very simple model for our very complex FMO complex, and now I will try to understand Photon-Echo even on a simpler system. As I mentioned, there are 3 laser pulses. What we have to care about are the delays between the pulses. The first delay between the first and the second pulse is normally referred as a coherence time, because at that moment your system is in a coherent state. Then the second interaction comes into play, you put your system in a population state, and this big T is normally referred as a population time. And then there's a third interaction, there's a signal emitted at a certain time T, and this time T is the detection time, we will refer it as a detection time. So, and we have a way to calculate our nonlinear polarization in our particular phase matching condition, and it will depend on detection time and on these 2 delays. So what's going on in the 2-dimensional Photon-Echo, you just take this polarization and do 2 Fourier transforms. One Fourier transform goes over detection time, another Fourier transform goes over coherence time. And then here is just an example, a schematic example. If say you have a certain ground state and then 2 excited states, A and C, I think, yeah. Then this is approximately what you would expect from your 2D scan, and this omega tau frequency is often referred as absorption frequency. So you have 2 possibilities to absorb, to A and to C, and you have 2 possibilities to emit from A and from C, and these states are coupled. So even if you absorb to C, you can emit from A, and this is how the cross peaks are formed. So the cross peaks will always show you that there is a certain coupling. You don't really know what kind of, but there is a certain coupling between the 2 transitions. If we continue with this very simple system and just forget about everything else, like the phase and environment, whatever, and want to calculate our polarization right away, so what we get, it looks like this, and this has to be Fourier transformed over time tau and time t. So this would be a delta function because we have no dephasing here. But this still explains you that you expect at the diagonal. This will be now diagonal terms. Yeah, just coming from the Fourier transform of this polarization. On the diagonal, you have always this frequency, the transition frequency to A and to C, and they will have intensity proportion to the dipole moment of this transition, of that transition, these 2 peaks. And then you will have 2 off-diagonal peaks here, with the intensity proportional actually to the both dipole moments terms. This all for the population time equals 0, so no delay between the second and the third pulse. Interestingly, if you now want to see what happens when the population time goes, and this is where all this coherence story comes from, is that if you consider the phasing contribution, so for tau larger than 0, then you notice that your off-diagonal terms will oscillate with the population time, and the frequency of these oscillations will be the difference between the 2 excited states. Yeah, that's why 2-dimensional Photon-Echo spectroscopy, because you have a way to more or less to detect the off-diagonal elements of your density matrix. And this was now just the 2 states here, but we can of course do the same thing for our exciton model. So we know what we get for 2 excited states. Let us have a look what we get for CERN exciton state. But we can already guess from what we learned for these 2 excitonic states, if you want, that we will have a number of cross peaks, and each cross peak will oscillate with a frequency which is the difference between the two transitions the cross peak corresponds to. So this is a calculation of a two-dimensional Photon-Echo signal for zero population time and very, very small dephasing. So we call it idealized resolution conditions, and I show you again just to so that we could see all the transitions and all the cross peaks corresponding to all these transitions. So the picture here is very clear. You have here transitions to the lowest state, and then all these diagonals showing these frequencies up to the 7th one, and all the 7 transitions, they share common ground state. So there will be, for every pair of this transition, there will be a cross peak. And we expect each cross peak to oscillate with frequency corresponding to the energy difference. Then you can add some broadening, and for some reason GCP even thought it will be a nice thing to put it in the cover, although they just rejected the first version of the paper. Yeah, so there's just a little bit of broadening added here, so you still can see this particular, each cross peak, so to say, in particular. But this is not really what we see in the experiment. Still, we can have a look under this still nice resolution conditions at what is going on with cross peaks and what is going on with diagonal peaks. And here I would like to underline that these calculations have been performed by a student of mine, and I just wanted to do it fast. So we didn't even do the full Redfield calculation. So these results are all coming from the very simple rate equations. Well, so we don't expect any coherence transfer here. And looking at the cross peak, we of course see the oscillations. These oscillations actually in our tests are not influenced by the dephasing between excited and the ground state. Yeah, the dephasing which broadens the whole spectra. I will show you later how it looks like. But if you still look at the same point of your spectra, even if it is broadened and you don't see the cross peak anymore, it seems that the oscillations will not be influenced very much. Of course, if you would increase the dephasing of the coherence itself, your cross-peak oscillation would also decay and more or less the same time scale. And this is why the two-dimensional photospectroscopy is so beautiful, because it really can follow, has this potential to follow each individual element of diagonal element of the of your density matrix. Yeah. So now it's diagonal peak, and this is something what we got when we just increase our dephasing, so we broaden the whole spectra. So what happens is we get oscillations on the diagonal when we just broaden the spectra. And our explanation at that time that we just get overlap effects. So our cross peaks become so broad that they can influence the diagonal peak, so that if we look at the point where we expect to find the diagonal peak, we see some contribution of the neighboring cross peak oscillating. This was our explanation. Good, fine. Now, this is our best fit of this experimental results. I want to mention that we don't take into account the excited state absorption. That's why we naturally miss this negative contribution here. And that's why our results look more or less symmetric, at least for zero population time. What we tried to get is dephasing rates, and also this diagonal elongation to be as close to the experiments as we could. And then if we take into account all these dephasing processes, what we got at that time was this result for the cross peak still survives the oscillation on the, influenced by dephasing processes, but still there, and absolutely nothing for the diagonal peak. Now that's a kind of summary we have at the moment with the FMO system here, or we have, to put it in other words, we have the experiments on the FMO system, and then we have the simulation on our exciton model. And compared to these results which we used to have before, it was very clear that something else enters here, we thought. Now if I look at these results, well, that's more or less nice. It's just we have to maybe, put it like another way around so we get some rates here. Not the exponential decay, I don't know. Good. So now the open questions I have is already?
Yeah.
Oh, can't be. Okay, then I will have to skip the open questions.
Well, you can discuss them.
You can use those as the basis for discussion.
So I'm still not sure, but if we can use, or if we can think about the FMO complex, for example, the antenna complex in terms of excitons, and if we can, well, then I will address probably only this part. It's nice to see have a look at long-time dynamics and kind of incoherent excitation. And if not, maybe we should also consider some Eboronic effects, but I promise not to talk about this today. No worries. So just maybe a couple of more graphs. These are the two Redfield simulations, full Redfield for harmonic bus. This is with the experimental pulse, and this is with the pulse which is 100 longer than this 30 experimental femtoseconds. And this is the dynamics which goes to 10,000 femtoseconds. Yeah. This doesn't seem that there's many difference in the exciton population dynamics. So these are exciton populations, diagonal elements of the density matrix. If you have a look at the local populations now, and the side basis population, of course with the short pulse, when you excite all these coherences, then you have all these oscillations, and with the long pulse you don't excite all these coherences, but still the population dynamics looks very similar. There are like three sides I have chosen, and they just follow each other, just no oscillations. Okay, this I skip. This I also skip. Now, I was not going to talk about it. I just planted there. Maybe someone is interested. Just because if you take vibrations into account, you will see also vibrations. But maybe you know this in the two-dimensional electronic spectrum, they will oscillate, and then you will have many frequencies for the cross peak. But then that's fine. So that's a kind of a summary. So we have our beautiful experimental technique, which in principle allows us to map the system density matrix, if you will, couplings, coherences, the phase and relaxation. I think there's still some challenge to interpret them. Then, if we consider our exciton system, well, exciton coherence of course exists, and it can survive over a very long time if it is created. Yeah? So the question is, if it is naturally created in photosynthesis. Then, well, the influence of the coherence environment, at least what we see, well, normal temperature depends on the spectra, and more or less what we expect from the environment happens. There's a nice method I always advertise if you want to do any kind of nonlinear spectroscopy, go and implement it. Yeah, and just to mention my favorite topic, my vibrations topic, if by chance you do excite some vibrations, you will see them everywhere, and also in two-dimensional photon aspect. I want to thank my collaborators and financial support, and all of you for your attention. Thank you very much.
Thank you very much. Questions? Actually, I have a question. When you compare your calculations with Greg's results,
Yes.
how do you fix the bar parameters?
Well, I cannot fix the bars parameters because I have no idea about the bars. We always have to make a certain guess. And I know that Redfield had been criticized, but I don't see the point why. Because it does allow me to be in a regime where coherences are excited, where they survive. If I want to look at them, I can. Yeah? I do have in the full Redfield treatment, I do have the coupling between the populations and coherences. I don't know if I really have to make it stronger. I also, at least at the point of my current understanding, I don't know. And when I fix the bars, since I do Redfield, I of course keep it weak. Yeah, but for the problems we're interested in, it seems to be reasonable. Yeah.
So you took them as fit parameters and optimized them?
Oh, no, well, I have presented just also the rate results, just rate equations results, and then we just took some parameters from literature. It's just a certain set which I always have an ohmic spectral function for the bars, so I can always guess where to put my cutoff frequency, just like, well, what kind of frequency vibrations would have in what region. And then I know that if I integrate the spectral density over the frequencies, then this is what determines my system bus coupling, more or less, and I have to keep it small so that the second order perturbation theory works.
And temperature was 77 Kelvin?
Yeah, yes, I think so, yes.
One question, yeah.
Two questions. Your calculated spectra are all on the rephasing side, and then the second question was, how much do you expect the sort of excitations to the double exciton manifold to impact the sort of positive region that you're calculating?
Okay. I don't have calculations to give now the exact answer for this excited state absorption contribution, but at least what I tried to check kind of analytically, it must not influence so much the lower part of the spectrum. The first question, we do not separate rephasing and non-rephasing contribution. Our calculations, we calculate from minus infinity to plus infinity, so to say, so where everything has decayed. Because this is also something I don't completely understand with rephasing and non-rephasing. I know that when there's no pulse overlap, they have non-rephasing and some rephasing, but they always have something in between, so at the moment I prefer to scan the whole region.
I think the possibility to include vibrations that you pointed out is very important. The usual excuse not to put them in is, everybody would agree that they excite a vibronic state, not a vibronic state.
Exactly.
We usually say the reorganization energy is so low that you don't have to worry about it.
Yeah.
On the other hand, you are in these simulations of Uniclinica to show very pronounced oscillations. First, I will throw them out, they're probably artifacts. But really what he sees is our skeleton motions, usually 1500 wave numbers. So if you put in some skeleton motion around 1500 wave number, typically 20 femtosecond, what prediction could you make that one should actually see in the signals? How would it qualitatively change as if you put them out? I mean, because that would be a prediction experimentalists could look after.
Well, it's just that you can you know what happens when you put vibrations in. Yeah, as you exactly told. It's just that you get vibronic states. Yeah. When you instead of this 7 excitons, you will have like a more dense structure. Yeah. If you if your vibration enters the
yeah, but I mean just the signals. If you turn slowly on the shift of the vibration, the reorganization energy. How would they evolve? What would be the qualitative difference? Well,
this is what I'm trying to answer, because the principal difference between vibronic state and exciton model is that you get also your ground state manifold. if you treat vibrations explicitly, then you don't have a single ground state, you have manifold. And then you have all these excited states, yeah? So, and the 2D spectroscopy will also probe this ground state manifold because, I don't know if I have somewhere a picture to explain it more, but what happens is that you also, when you probe it, you have a kind of you go from the upper states to the lower states, yeah? And then the excitonic systems, you can also only probe to the one ground state, yeah? If you have manifold, vibrational manifold in the ground states, then you can probe also to the upper states. And then the whole spectrum will get much more complicated because your frequencies will be very close to each other. So it will be extremely difficult to say where is your diagonal, where is your off-diagonal, and how many things are on the diagonal. So at least for the model calculations, which I used to do for these vibronic systems, what we see that if we take a point which is kind of on the diagonal, even there we have many frequencies that contribute because all these different pastas comes to this point because of all this, you have way more possibilities there, yeah.
I'm just concerned about leaving out this 2-exciton manifold. If I think of two uncoupled two-level systems,
yes.
The reason I don't see a cross-peak is because of interference between the stimulated emission and excited absorption, which goes through the 2-exciton manifold. So in your theory, do you predict cross-peaks between uncoupled systems because you don't get that cancellation?
I think I would, yes.
Okay, so all these cross-peaks that we're seeing here can't be mapped on the coupling because they would come if we're completely uncoupled as well?
That's true, of course, but this is something I have to think more about, but at least I always thought that we can really realize, somehow understand the dynamics and how it is reflected into the without excited state absorption. But mine might be wrong. Maybe
well, I don't disagree that the dynamics should be the same, but comparing these two spectra,
yeah.
where you can't eliminate that term in the perturbation theory expansion. That's the only part that I have a real problem with. It's a two-dimensional response. It's just not one that's measurable.
Yes, I see that you have, instead of going down, you have always this possibility to go up.
Right, so because it would be wrong to assume that the only contribution of the 2-exciton manifold is above the main diagonal. It's true that that's where you see a stronger aspect of it because of the dipole moments, but that's why you don't see certain cross peaks below the main diagonal as well. In particular in an uncoupled diagonal.
That's true, of course, but at least, I never tried to, so to say, to really get exactly the experimental results, but I just was trying rather to understand the principles and what I have to have in my dynamics in order to get it in the spectrum, and I hope that it's more or less fine when I look the excited state absorption. Or drop excited state absorption. There have been many questions there.
Yeah, there are many questions. Unfortunately, the time is running a bit short, so I suggest that we discuss this in the coffee break also. And then we thank